for today, I'm talking about how functional programming in Scala can meet feature engineering. And the essence of the talk is how FP in Scala can meet any real-world problem, not just feature engineering, but I took feature engineering as a use case to demonstrate how it can really meet without too many complications in picture. About me, I'm Afsal. I'm from Sydney. I work for a company called Simple Machines, and we are a consultancy, bunch of functional programmers, passionate about functional programming. We write Scala, but we write everything. We are technology agnostic, and we kind of specialize in streaming, big data, data engineering technologies. And thanks to Simple Machines, they brought me here. And thanks to Scala for giving me this opportunity. It's great. And before I start, thanks to ZioConfig, which is a library that I'm working on with Zio organization. The reason for that is I'm using the exact same pattern which I used in ZioConfig for this particular use case that I'm trying to explain. So, and I found it really exciting that it can solve many real-world problems relatively easily than other patterns that we usually see in FP in Scala. All right, so why functional programming in Scala is made difficult? I should say it's made difficult because we are hit with a ton of jargon. And there is no point in explaining what each jargon is, but you know what it is. And then you have, you know about implicits. Tons of implicit, inductive, implicit resolutions, and the whole design is based on implicits in your application code. Implicits are powerful. Implicits are really useful, and I have used it, and I'll still use it. Sorry for that. But do we really need them in an application code base? So it's a question that you need to ask yourself. And how much it can impact in a team where there may be people who don't know functional programming. But they want to know functional programming, but there is a sort of hindrance somewhere. And type inference in Scala is another issue. It's an issue if you're not dealing with it properly. Are we using the right tools? Are we using the right libraries that fix type inference issues properly? Or are we dealing it ourselves, making it much complex, fiddling with compiler, taking time to solve a problem? And then type class specializations. I love that topic, and it's debatable. Given a problem, we see, oh, that's a common add. Oh, well, that's a prism. Well, that's an invariant applicative functor. Sorry about that. Yeah. And we tend to lose in that type class hierarchy space because suddenly your problem changed. Oh, it's not anymore an invariant applicative functor because there is an error in the right direction. Oh, then it becomes a prism. Oh, can we make it optional so that it's a prism now? And it's just going somewhere else other than the problem. And we love free structures. And I really love free structures. It was a great experience for me working with free monads and free applicatives. But are they really free? It comes with sophistications. It comes with a hell of libraries out there to solve boilerplate. And to understand what those libraries are, you need to understand what those boilerplates are. And to understand those boilerplates, you need to have a wide set of knowledge, which is not probably not a good return of investment in a workplace. And there are many options of solutions. There are many solutions. Oh, I could have done that using recursion schemes. Okay. And the result is slower development of incomplete FP in the small solution. You can see a lot of traverse and monoids all over the place in your code base, but it will fail in runtime. And the manager will ask you, so what was he doing? And what is the solution to all of this? If we stick on to the fundamentals of functional programming, we can make things faster. And in fact, ridiculously faster. And the fundamentals are quite simple. We need to stick on to referential transparency. You know referential transparency. An expression is E is referentially transparent if for all the programs P, if that E can be replaced with the result of the value, such that the program behavior doesn't change, which means it's super powerful, right? You can simply go ahead and refactor your code base. You don't need to worry about anything. It will work as you intend, because that is referentially transparent. And it is backed by pure functions. A function f is pure if that expression f of x is referentially transparent for all referentially transparent x. And again, makes you much confident in dealing with your code base. And total functions, you need to handle everything, right? So you need to represent the absence of values. So when you query a database, you need to see, you need to handle the absence of the value that comes off from the database instead of giving a null pointer exception. Lawful abstractions, and please don't get carried away with the word abstraction. A set of descriptions that tells what exactly is your application without having to deal with the details of the backend engine that you're trying to use. And let's make that small little set of descriptions which are composable lawful. And then that laws will get propagated through to the details of your code base automatically, and you will get a high quality code base. And if all of this is backed by type-driven development, what happens is it's a faster development with pure FP solutions. It's FP in the large. And this is something which I learned, especially over the last last maybe year, especially when I started joining CEO channel. I should specifically mention that, because I was dealing with that and moved to this. And thanks to everyone in CEO. Thanks to John for his mentorship, because some of the patterns that I'm using, it is, thanks for shedding those lights to those patterns. Okay, so stories behind. Let us write a big data problem, an FP solution for a big data problem. This is not any library that we are trying to build. It's just an application code base handling all the real world requirements. So what is this problem? So you have billions of clickstream events coming into your application. Let's say it is a banking application. And there are millions of customer account data set. There should be millions of payment data set, you know, the usual big data. And then you do business analysis and machine learning on top of it. So what is the problem? So we need to find the attributes of customers from this big amount of data set. And there are solutions to this. We know there are Apache Spark and Beam, and you know, there is a dozen of them. And we need to find the features or attributes. And an example is total account transactions for each customer in the last 3 weeks. That's an example. And we are going to call those attributes as features. And then we need to build a very simple interface. Even if it's not a library, you need to provide a simple interface for either the data engineer or the business analyst to quickly add new business logic into your code base. And it should be combined with a thin API to compose all of it. Like, it's just not a list of features. It'll be a list of features, and it'll be an interface to compose them properly. And what does that mean for us? We need a thin layer of interface, uncluttered with performance details. You need to quickly add new feature logic into it. And it should be accompanied by a thin API to compose your logic, and it should be declarative. Remember, when we make things declarative, we forget about performance. We talk about easiness, but it just fails in the cluster. And we don't want that. And optimizations, which is otherwise pretty complex with handwritten language of the data source. Like, sometimes it is quite hard to satisfy all your performance-related details in a SQL query. Because you're adding new logic, you can't go and edit an existing SQL query, and then you have to test that. So how do we handle that? And it should be fairly backend agnostic. And I've taken a very small piece of problem from a wider problem to demonstrate the use of functional programming in Scala. I can't go and solve all the big data problems here, so you might have lots of questions, and I'm ready to answer after the conference. And we don't have a year to make it happen. You have a couple of weeks working as a consultant. Oh, you've given 2 months, solve it and go. What is a simple feature definition in SQL? So we are trying to find the maximum, the sum of credits of each customer in their account in the last 14 days. Very simple. Can you see that? Right. And in SQL, that is select customer ID and sum of credit. If the credit is a null, you replace that with 0. And then, we tend to do that last 14 days in the feature name itself, sum of credit 0 to 14D. From input table, group by customer ID. We are always going to do a group by customer ID, by the way, because it's a customer and the sum of credit. And for the last 14 days, so you have some timestamp operations in your SQL. It's like a pseudo SQL. It doesn't compile. It doesn't work. But we could reduce it down to a few important points. Sum of account balance, so sum of credit, whatever you call it, and from input table, and last 14 days. You're always going to group by customer. And in short, that is a sum of credit as some credit from input table for the last 14 days. And we hate that name, so let's fix that, sum of credit. I know it's going to be last 14 days for this particular query. So let us express this in Scala. Okay, this is a very naive way of thinking, right? Oh, okay, I've got what I want. So the feature definition will have some input. At this point, I don't know what that input is, but I know that's an input parameterized by some dataset D, and I don't know what that dataset is. I'm lazy. And then there should be an operation that can operate on the dataset, and let's call it as an expression, like E. That's also parameterized, polymorphic. And we need to find the name of the feature, and then we need to provide for what partition of the data that we need to query on. Partition is nothing but if you specify a partition in your dataset, so if your dataset is stored as partitions, and if you specify a partition, you'll get a faster query, faster performance. And this could be an input, right? It could be a constant input, or you provide a directory, and both of them are inputs. And we have some helper functions that says, given a string, get me the data, or it could be a constant. Like for example, if you know Spark, your constant could be a constant data frame. You already got that. You don't need to do anything more to get it. And that's the feature definition expressed in Scala, sum of credit. It looks exactly the same. And you can also do complex input, because our input is just a description, right? A directory of input table may be joined with another directory of another table. I've skipped some details. It could be a left join, it could be a right join, it could be outer join. So let's say join. And if you don't have any of them, like if it fails, maybe orals a constant data set. So you can have a complex input. And let's have a list of them, okay? So we have some very simple case class that represents your feature definition. So it could be a sum of account balance, a sum of debit, and many features like minimum of account balance, maximum of account balance. In the last partition. And now the fun part is we need to compose them. So is that about list operations? We'll see what that is. The minimum thing that we need to do is, given a feature definition, we need to represent something that can execute something somewhere. And that's feature gen. I'm going to generate features, and let's describe that thing. So this is feature gen. So I'm going to start the job. Given a feature definition, I'm going to start a job represented by feature gen, and it is going to return me some kind of feature result. And even at this point, it is lazy. Nothing is getting executed. You're describing what you want. And the feature result is consisting of some data set. Maybe it will have a customer, and it's not maybe. It will have a customer, and it will have the value of the attributes. And it will have metadata. And one thing that I learned is, if I'm considering metadata at a later point in my project, it'll never happen. So metadata from the beginning. So metadata is a list of feature details, and a feature detail is nothing but a feature name, and it could come from a variety of sources. It could come from one source directory, and then you derived put some queries on top of that. So there is so much of propagation of data set happening at different points. You need to combine all of that. We will not be dealing much with the metadata for this talk, but please remember feature result. It consists of some data set that represents a customer and the value of the attribute. Now let's extract the structure of our problem. Okay? Let's say feature gen is a simple trait. It's parameterized by some data set D, some expression E that can operate on that data set, and whatever operation that you provide inside that structure is going to give me some result A. Okay? I know there is map, map2, and there is a zip operation. We'll discuss all of that, but forget about that for the time being. Just that much, feature gen. I have explained that. D is data, E is expression that can operate on data, A is a result of the computation. And let's implement this. The first one is pure. Pure was in fact the last thing that I wrote in this code base. So let's go with the second one, zip. Zip takes one feature gen and another feature gen. They produce A and B respectively, and returns a new computation which can give you A, B, a zipped version. And there is an interesting bit here. They are not runtime values. They take two computations in that node instead of two runtime values. If you have two runtime values, all that you can do is zip it, nothing else. But here we get two computations. Now you know how did we end up in that zip. So it'll be useful later on. And then you have a map function, which means given a description that describes your feature generation, that returns a value A, and if you know how to go from A to B, then you can map it and get a feature gen of DEB. And creating the features is nothing but given a feature definition, the logic of the expression, start creating the features. Again, lazily. It's still descriptions. It's not executing anything. And the last and the most important bit is joining the features. It takes, again, two computations, not runtime values. Because if it was taking two runtime values, all that it could do is join it and then give it to you. Instead, we are taking two computations for join features node. Okay? And we'll see a use case of pure. And we have a set of helper functions to compete with the type inference, and I find it really useful. And you don't want to expose the guts of your data structures to the users. So start means delegates to create features. Pure means given any value, it just lifts to your feature description, feature generation description. And then fail means given some message, I'm going to fail it. And at this point, I have no idea how I'm going to fail in real world. I'm just describing things very naively. And then I have a join. Again, it takes two computations and delegates to the join node. And in fact, sometimes you might have a list of such computations, a list of feature generations to be done. And then you want to convert that list of feature generations to be a feature gen that can give you a list of result. And let's call, or maybe it could be, in this particular case, it's combining all. Like, if you have a list of feature gen, I'm going to combine all of the results and then just join it. And I'm doing a very unsafe operation, which is computations.reduce. It can fail if the list is empty, and then call join function. This is something I explained. A sequence, you have a list of feature generation that returns an A. And if you call sequence, it converts it to a feature gen that can return a list of values. So a list of feature gen converted to a feature gen of list of A. For those who are familiar with Traverse, probably you know what it is. But even if you don't, it's fine. And then we are going to say collect all. which is sequence itself. Now let's compose. Okay, is that list of feature definitions enough for us? Let us compose this program using the list of feature definitions that we have. So a job is given a definition, start the job. And how about joining? So you have one job joined with another job. I'm not saying one data joined with another data. I have a job that should be joined with another job, joined with a third job. Because that join is always going to be, if you can think about it, it's an outer join. Like every job is going to emit a set of customers and their attributes. And then if you want to join with another job that produces the same kind of data set, you do an outer join because you don't want to miss the customers because some attributes are not there for some customers. So let's call it as join. And there won't be any left join or right join. It will be always outer join. And let's call it join. And we will collect all of the features, right? So sometimes you have 3 or 4 jobs joined together, and you have a 4th job and 5th job. So you have a list of feature jobs, and you collect them together to get a feature job that can give you a list of results. And sometimes you will combine, which means join. That's another way of joining it. And sometimes you will map. If you say, this is how I want to generate some features of the customers, and then I'll map over the result and get the metadata size, for example. Or maybe I'll discard it completely. So you can do anything with that map. And let's now run the feature gen. So how do we run this? We have an abstraction. We have a set of descriptions that tells how to create features. But now let's run this. So instead of running it to the values, instead of launching the missiles, we'll say, let's run this to 0, which can then talk to the real world. Because we will need a middle layer right now. We need a purely functional FX system in between. So, and we don't want to keep doing it every time. So we'll have a one single implementation that runs this feature job to a target effect. And we are using CO for that. And there are several reasons. I can go on and on, talk about it. But mainly, there is no implicit requirements. There is no implicit timer anywhere. There is no it's relatively easy to use, especially in terms of the concurrency operations. Expressive types. You have the type saying that, oh, this is always going to fail, or maybe I have to handle errors. You have a very well-defined typed error channel. And it's awesome type inference. The mental model of CO, John has explained this day before, and it's relatively simple. It's parameterized by R, E, and A. R is environment. We'll have a talk about that today. E is error that can happen in your computation, and A is a final result. So what that means is, given some input or given a context where you have enough inputs to run your computations on, your computation can either fail with a error E, or it can return with a value A. Okay, enough of CO. Now let's convert our feature gen abstraction to 0. And in our case, that target FX system 0 has got an environment called data service. That environment knows what exactly needs to be done with all the nodes in your program. And that's our implementation. This is just type aliases to make things a bit more readable. So that's it. Feature gen, represented by data, some expression that can operate on the data, and that is converted to analytics task. We are calling that final target FX system as analytics task, and that is nothing but CO with an environment called data service. And running that is nothing but returning that implementation, which means an arrow that goes from feature gen to analytics task. And what is data service? Coming back to the previous slide again. We said the environment is data service. So what that means is a simple interface. Again, that interface it's still pure. I mean, in the terms of It doesn't evaluate anything. It is all going to return a 0 in return. So given some input, how do I get the data? I know how to do that. Like if I know Spark, I know how to do that. So given some input and given some partition, which is optional, like you may or may not have partitions, get me the data. Generating the features, if you have an expression, like in Spark, it could be a column. So if you have that feature definition that encapsulates those logic in it, you know how to create the features. You know how to emit a customer and the attributes. All of them are one-liners, and I can show that actual implementation after the talk. And joining to a data set is also simple, because since it is all outer join, and if I know how to do outer join using a data source language that you know, that's also a one-liner. And projecting the features is quite simple. If you know select, and that's it. Like, given a data set, you select the explicit set of expressions out of it. And all of them returns a task, and task is 0 with error as throwable. And you can have your own errors to make it much more safer. And let's run this. How do we run it? Given a feature gen, how do I convert that to a 0? Quite simple. You do a pattern match on each of the node. Pure value means you lift it to 0. And zipping 2 programs, not 2 values, but zipping 2 programs is recursively calling apply, which will give you a 0 in return. And 0 has got a zip function in it. And apply the second program. And you get zipped values. Mapping, simple. Apply the program, recursively call it, and map it, and apply the function, if. We didn't talk about join features, so let's talk about that. Joining 2 features is joining 2 computations, isn't it? So F1 here is a computation, F2 here is another computation. You apply both of them, recursively call both of them, and zip it. And now you've got 2 feature results. And now you access the environment, which is a data service which knows exactly how to join the features. So you access the environment from 0, and then call join. And during that process, you accumulate the metadata once and for all. So this conceptually means that whatever backend that you're trying to plug in, you will definitely accumulate the metadata. So you will not write code in terms of backend engines to accumulate metadata. You have already done that in terms of abstraction. And let's create features. So creating the features is, given a feature definition, you access the environment from 0. And the environment is a data service which has got a function generate feature. And you provide all the information that is required to generate the features, like input, operation means the logic, and a partition, and form the feature result, which is a case class. And we will run this with Apache Flink. Okay, so how do we do that? So we have a list of feature definitions, a sum of credit, max of credit, and the same set of features for different partitions. Last 2 weeks, last 2 to 4 weeks, and last 4 weeks. Okay, and you keep adding them into the layer. And executing this is quite simple. You define the data service for Flink. For Flink, data means a table, and expression means Flink expression. And that is literally 11 or 12 lines of code, which can run in production. And this is a simple composing, right? You combine all of the features. So you have a list of features, you map it, and then start the job. When I say start the job, it's still lazy. It's just giving you a feature gen in return, and you combine all of that. That returns a feature gen. So you have a description that says this is how I need to compose them. And we have run function. You know run function. It goes from feature gen to 0. So which means a run function takes a feature job. So I'm calling that run with a job. That will return you an analytics task, which means 0. 0 needs an environment called data service, so you provide the Flink service. So you're literally running this now. Not yet. You have to run 0 explicitly. So still a description, but yeah. This is to kind of a proof. Probably may not be much useful, but I'm actually running this with Flink. And the only way that I found seeing the execution plan is to emit the execution plan as a JSON and copy paste that in a Flink plan visualizer. And it returned a very big execution plan. I don't know what that is. I can see there are a couple of aggregations, like 6 aggregations. Joins are happening. Like, I don't want you to understand each bit here. Like, it's a big, I couldn't represent that in a single slide. So I thought of taking it as a video. And that's a simplified version of it. So you have a data source, you're having 6 aggregations on top of it. And there is something nasty here. We said we have 6 features, each of them have got their own aggregations. And then I have emitted a query which is nothing but in Flink, a.join, b.join, c.join, d. And how do you want that to be executed? So it seems like it first executes a.join b, outer join. And then once that is finished, it will then join with the third one, while the third one was still waiting. And it will wait for the last, like all the 5 joins are very sequential. You could have done that in parallel, isn't it? Because it's an outer join, because you're not anyways losing the data. And if you can think about it, like if it is 1,000 set of features, this is going to be not running in production at all. It will run up until 100 or 200 features, business will be happy, and then it will fail. Unless you have money to increase the number of nodes. And we hit the first real world issue, and the worst execution plan is a sequential outer joins. So let's be pragmatic. We have got a list of feature gen, and what we could do is we can explicitly say slide over 2 elements and then join each one of them and do a divide and conquer using recursion. So list sliding 2 and 2, which means you can have left and right. You may or may not have left and right. So if you have both those sides present, you join it. If you have only one side present, you leave it as it is. You have the right side present, yeah, same logic. And otherwise, can that happen? Maybe. You've provided a list. So it's a good time to change that to const, which is a non-empty list, so that I don't want to handle that problem. So you better do that. And that's more of a detail. We'll skip that. And you keep doing it until it converges to one single point. So a list of feature generation job, sliding across, joining it recursively. And I'll call it as a pragmatic approach. We'll see why. And of course, I'll show you the execution plan straight away. You can see 3 joins done in parallel, unlike the other bit. And less number of arrows, a little more constraint, a little more small. And that's what we achieved. We parallelly joined a pair of features, 3 pair of features, which is faster. But are we done yet? Why do we need to join? Like, why do we need all of these aggregations? 6 aggregations in parallel. We had that because we exposed a declarative interface. You kept adding new features, and you have an aggregation job per feature. At this point, you've already deployed your job. Business is kind of happy, and we are moving ahead. But right now, you have written a good code base that is scalable enough. Like, even if you have more problems in future, you can quickly change it. Go and change things fairly quickly without having to worry about what backend engine is it. The next thing is we could reduce the number of joins. So this time, we are not going with this pragmatic approach, and instead we'll go with a little more interesting one. It seems we can introspect the program. And this is where it gets much more interesting. We remember the join node in your program. It takes one computation and another computation. That's feature 1 and feature 2. They are computations. And thinking about if I can avoid this join is nothing but I don't want the right side. Can I squash the second computation along with the first one such that this node doesn't exist anymore? That's invalid, right? You don't have a right side to join. What does that mean? So you have written a description that is fully introspectable. Like, given a program description, you know what exactly user has done, like what they need, the way they're composed, and that means you can get a summary of the program. So given a feature gen, I'll call that summary as a set of feature requests. And we'll see a very nice first-time representation of feature requests. To begin with, let me talk about this white table. So that is nothing but you have a customer, you have an attribute, and you have different jobs. You combine them together like outer join. Now you have a white table, and this white table will have thousands of features in it with the customer ID. And I know that this job is something related to the white table, so let me represent that using simple Scala map. Okay? And not the backend engine data frame. Okay? So these are some of the small little subtle concepts that we need to imbibe. The key is nothing but the input and the partition, and you have a list of expressions that can run on top of that input and that partition. And what do you call by merging those two features, merging those two white tables? Data frame.join another data frame? No. You simply combine two maps. And here I've used monoid to combine those two maps. You can actually combine it explicitly, like it's just about, for that particular key, combine all the list of expressions that needs to be run on top of it. If you don't have a monoid instance, do it explicitly. And we merged in terms of map and not in terms of data frame. And executing this is nothing but you iterate over the map and then create the features and you combine all of it. Now you've got a feature gen that represents a white table. Now, what is a feature request? So what is a summary? Maybe it is a list of such white tables. User might have created, as part of his program, he will be creating a list of white tables there. So the developer might have done anything, but I'm just assuming that this will be a list of white tables. Combining two feature requests is adding those two lists. And given a feature definition, adding it to the feature request is nothing but we can convert feature definition to a white table because it has got all the information that requires to be a white table. And then you add it to the list. And merging two feature requests is nothing but you've got a list of feature requests, and you've got another list of feature requests. You flat map over the first one, and then you map over the second one, and you do merge on top of it. So when I flat map, you get a white table. When I map it, I got another white table, and then you merge those two white tables. I know it's confusing sometimes. So let's do this, okay? User might have done a feature request, feature gen, and I'll do the same pattern matching. So if I have a create features, I'll add them into the request. If I have join features, I know that those feature requests has to be merged. Mapping is simple recursion again, go, keep going. And zipping it is don't merge it because user didn't tell you to merge it. Even if it is a feature definition that comes in the same white table, it's still not yet to merge. And by this time, all that you need to understand is we were able to go through the program and create a summary of that program. And if you have that summary of that program, which we represent it as a feature request, and a given implementation, like a base implementation, which is going from feature generation to analytics task, you can get a new implementation, which is a much more optimized version of the base implementation. That's the concept. And another important bit is we didn't have a node called flat map. Because if you had a flat map in it, you wouldn't be able to get a summary out of it. Because flat map needs a runtime value to get into the next set of computation. And we don't know what that runtime value is, so we'll skip flat map. And we have skipped it, and hence we could do a program introspection. Now you can use this summary to optimize, to return a new implementation, which is an optimized version of the base implementation. So you have a summary, you map over the summary, which means you got the first white table, and we did see an execute function inside that white table, which represents a feature gen corresponding to that white table. And if you have a feature gen, you can use the base implementation to run them. Now you have got a set of pre-joined data set. You've already joined all the data sets. And now I need to return a new function, because we need to address what user has composed. For that, first we'll pattern match on the create features, and then you look up the pre-joined. Hey, have I done this before? Have I created this before? Maybe look up, and then you pass it on. And if you have already created a feature and the user has asked that feature again, you may not create it again, because I'll say, I'll fail it. I have done this before. So create features right now may or may not give you a feature. For that reason, join features, which is two computations, now need to handle the absence of features, because join features, remember, it takes two computations. So it'll compute the first computation and it'll compute the second computation, which will end up in our base termination condition called creating the features, which right now may or may not give you a value, which means either side of this join features may be absent. So you've kind of got rid of join. That's more of a detail. I need to keep a state of what has been passed. I really don't want you to understand that much detail in here, but I can go through it. But I have used ZRef for the state management, just to point out that. And all that we are using in the entire code base is Zio and Scala, nothing else. And join is now interesting, isn't it? We said this. We apply the first feature, and applying the first feature will give you a Zio. Zio has got either in it, which will allow you to work on whether there was a failure or not. And you zip it with the second computation. Again, that can fail, because we said join features can now have computations within it that may or may not return feature values. So if both the sides exist, which means you have something to join, and then you join it using a base implementation. If only right side exists, you use the base implementation and then just lift that value. Now we used pure. And if both of them doesn't exist, if it's an undefined state, nothing to join, and failed, we'll do that for the time being. Let's execute this. Okay, to sum up, we have a feature gen, you have a run, which returns an implementation that goes from feature gen to analytics task, and then you can get a summary out of that feature gen, and then you use that summary, and we already wrote this optimize function. All that code that we have seen is optimize function. You pass that summary and an existing implementation, and you get a new implementation, which takes a feature gen. So you pass that feature gen, and that will give you a Zio in return, and that Zio need a data service. We completely forgot about the backend engine, isn't it? So we provide a Flink service. And let's see what this gives. Much better. Still not there in one slide. We have 3 joins instead of 6 joins. Or well, we have 3 aggregations instead of 6 aggregations, and hence we reduce the number of joins by 2. Like it was 5 before, and now it is 2. Okay? And the reason for that is we squashed 2 feature definitions into one single logic using the optimizations that we did, which is scalable, which is abstract representation of your optimization. But are we done yet? we moved away from pragmatism right now. So it seems we can do more. Because we have this super powerful way of introspecting the program. So I can look at the program in whatever way user has composed those features. I will know that whether one feature can be derived from another set of features if it is a monoidal kind of feature. For example, get me the sum of credits in last 4 weeks is equal to get me the sum of last 0 to 2 and 2 to 4 weeks, which means I need to calculate only those two features. I don't need to create an aggregation job for the last one. I'm not going to explain the code for this, but you can see there is a projecting happening. I'll create two features, I'll join them, and I'll project those two features as a simple addition. And that will give you this optimization plan, this execution plan, which is one join. So that really happened, and probably you can see that in a single slide. That's a Flink execution plan, and we'll talk about more than Flink now. So before was that, and after that is that. And as we have done that using program introspection, we took a different path rather than trying to do everything using list and data frame APIs. We were working in terms of abstraction. Too much code. Apologize for that. But let's sum it up in pictures. That's what you asked them to do. So when we composed the program, you had a join, join, join. You created two features, and then you joined. Created those two features, and you joined the result of that. That involved 5 joins. And in fact, that was after fixing the sequential join problem. And that's the after. So how did we find this stuff? Did we log anything anywhere? User has given some composition, like a description, and you just manipulate it, you changed, you do all the bad things for the good outcomes. But we'll see how we can log things in this program. Instead of logging it everywhere in your application, how can we do that? Before that, this is what we did. We had a program, and then we converted it to Zio, and you provided a data service. Yeah, I'm finishing it off. And then we optimized using a summary. And again, the last bit was flat map. Instead of a summary, we emitted another program which knows how to derive features from the underivable features, which means how to get last 4 weeks sum of credit using the previous one. So for that, you need a value. So first you took a summary, and you emitted the next program that needs to be run. So we created a program inside a program, and we used that summary for the first optimization, and then CO executed, and you flat mapped. That then converted it to CO back again, and then you finally executed using a data service. I know that's quite a lot, but if you go to the desk and follow the pattern and try and write it by yourself, you'll get it. And it's important to talk about laws. I said your abstraction should have laws, and that laws should get propagated through to the details of the code. So we can't write test cases for each backend engine that we're going to have. So for that reason, let's define laws in terms of abstraction. So one of those laws, one of the dozens of laws is, if you join two projected features, that's equal to projecting the join features because it's outer join. And it should have all the metadata involved in it. And whatever backend engine, which means whatever data service that you're trying to plug in, it will go through these laws, and if it fails, you have written a wrong implementation of the data service, which means you will never end up in a situation like when you join two dataset, ambiguous values, can't join. You'll never end up in that situation because your test case already captured that in terms of the abstraction. And logs is simple. It's a kind of AOP logs. It's an aspect-oriented programming kind of thing, but it is much more safer. Because it is just program, you can just pattern match on each node and then tell, oh, this is what I'm going to do. And then if you have a base implementation of how to go from a feature gen to analytics task, you first log it and then call the implementation. So before everything happens, it's automatically logged. And is there backend agnostic? So, okay, Apache Flink, how about Apache Spark? All the sequential join problems was there in Spark too. All the optimization worked in Spark as well. It was quite easy for me to change the definitions. All that you need to change was the expression in the list of feature definitions. I didn't want to abstract it further, and hence kept it that way. And what did we achieve? Things that we need to note here is no implicits, no macros, and no sophistications, no external dependency. All that you wanted to know is Zio. There was quite a bit of Zio involved in it, I understand. But it is very well documented. And rest is pure Scala, just Scala. And it was introspectable. And there is another way of doing this thing using free applicatives. And using free applicatives, you can bring in the free app from CATS or Scala C and then use the analyze function that returns to the monoidal target effect. And then you can use that using natural transformations to get exact same result. And no time spent on boilerplate. And no implicits, as I said. It's relatively 100 lines of code. And thanks. And questions. Sorry that I took time. Yeah. No questions? That's good. All right. Thanks, everyone. And thanks to Scala once again.